Hey, Bill, glad you made it. Guess what we're talking about today? Ohm's Law. Yeah, you don't care. Alright, welcome to the first video in the Tech Zero training program. It definitely looks like a first video because only half my body's in it at all times. So I'm sure you already know that this video is about Ohm's Law. Don't let the board intimidate you, but it'll all make sense, Grasshopper. So the first thing I'm pointing at is a tasty math pie stuffed with V's, I's, and R's. You gotta think of that vertical line as a multiplication sign. I times R gives you V. That horizontal line's like a division sign. For example, if you're looking for I or amps, you do V divided by R. Sometimes you'll see E or U for voltage. Not using that. Sometimes you'll see A for amps instead of I. Definitely not using that. And sometimes you'll see this horseshoe looking thing for resistance, and we are not using that. Point is, letters don't really matter, just understand the concept. Volts, amps, resistance, okay? What's in that circle right there is all you need to start on your path to become a troubleshooting master. So starting off with the big V, voltage. It's measured in volts. That's why I have a lightning cloud. AC or DC doesn't matter. Or you can think of Harry Potter's face. He fights Voldemort, right? Or Voldemort. I stands for current. Some French people made that decision and it stuck. Current is measured in amps, and it's what makes a circuit hot, temperature-wise. That's why there's a thermometer. Then you have resistance, and it's measured in ohms. That's the horseshoe that you'll find on your multimeter. Now that that's out of the way, I will explain the bottom left of the board. What I'm poorly trying to show you with my arms there is that if one of these letters stays the same and the second letter decreases, then the third letter has to increase. And when I say increase and decrease, I mean numerically. It's like a teeter-totter. We're going to use that example next to the teeter-totter on the left side of it. If the fulcrum, fulcrum, science word, the fulcrum is in the same spot, doesn't change at all. So current in this example is going to be our fulcrum because it remains the same. If voltage is some 400-pound guy who ate too many verpies and resistance is some 200-pound guy, voltage is going to be sitting on the ground. If resistance decides it wants to bulk up by eating V's extra snacks because V's about to have a heart attack, then V will go up and R will go down. And here's the pi math written out here. There's only like 3 possible equations you can get out of it. Learn it. So let's put this into action with our little circuit here that you need binoculars to read, so sorry about that. We have a 24-volt battery powering a 240-volt resistor. Pretend the resistor is like a light bulb or one of those sweet pill speakers. Take those numbers and plug them into the pi. So you got 24 volts on top. Bottom right is our resistor, so we plug in 240 there. So how many amps is in the circuit? So we're going to go ahead and do 24 divided by 240. If you don't know how to get these numbers, get a handy dandy multimeter. Set it to volts DC because it's a battery and measure your battery. Then switch it over to that horseshoe symbol, stands for ohms, and measure your resistor. Bada bing, bada boom, you know? So when we do 24 divided by 240, it equals 0.1 amps. That symbol with a question mark next to it is a fuse symbol. You might need to do this kind of math if you don't know what kind of fuse you need in your circuit. Now, if we change our 240 ohms to 250 ohms, I don't know, you plugged in a fan because you got too hot from dancing to your pill music. Like our teeter-totter, if voltage is still 24 volts and resistance goes up, current has to go down. When my hairy skull gets out of the way there, you'll be able to see that if we do 24 volts divided by 250 ohms, you get an answer of 0.15 amps. If you know your decimals, you know that that's a smaller number than 0.1. That's all I got. Okay, bye!